Hey everyone, grab a seat and welcome to today's huddle. I've been digging into some incredibly cool new data straight from Anthropic on how Claude actually manages computing power under the hood. And I knew we had to go through it together in this explainer. If you're like me and you've been using AI to help you code, you've probably noticed that, well, sometimes it gives you absolute magic, right? And other times, it kind of misses the mark. So let's dive in and figure out exactly how we can dial in our AI teammates' effort levels to get those consistently brilliant results.
Okay, let's jump right into the sprint agenda for today. We're going to cover unlocking test time compute, then look inside adaptive thinking, talk about balancing speed, cost, and quality, compare large models versus small models, and finally wrap up with our new best practices for coding.
All right, part 1. Unlocking test time compute and scaling intelligence at inference.
So, what does scaling intelligence actually mean in practice? Let's define this really clearly. Test time compute is basically any form of Claude spending tokens at inference time to reason through and solve a problem. For years, we've basically just assumed that training bigger models makes them smarter. But here's the absolute game changer we're seeing. We could actually scale intelligence simply by allowing the model to work longer on a problem right when we ask it. It makes total sense, right? It's just like giving a human engineer an hour to debug instead of 5 minutes. Letting the AI think longer drastically boosts its capabilities, whether you're throwing heavy software engineering at it or building agentic workflows where the AI has to take independent steps to solve a problem on its own.
Now, you might be wondering, how exactly is Claude spending that extra time and those tokens? Well, it actually breaks down into 3 pretty distinct slices. Slice 1 is thinking. This is literally Claude's internal monologue, its private scratchpad where it reasons step by step before actually doing anything. Slice 2 is tool calling. This is how Claude reaches out and interacts with the world, like executing a search or reading and writing files right in our codebase. And then slice 3 is text. That's the token budget it spends actually communicating back to us with summaries or updates. And all 3 of these are absolutely crucial to how it solves our massive coding problems.
To really see why this matters, let's look at this fantastic experiment the Anthropic team ran using Opus 4.7. They asked it to code a simulation of cars at a traffic light. On low effort, it took about 50 seconds and 4.6K tokens. I mean, it passed a test, but it was super clunky. Actually, it literally put the traffic light right in the middle of the road. But then when they cranked the dial up to high effort, which took twice the time and twice the tokens, Claude suddenly implemented an intelligent driver model and smartly moved the light to the side of the road. And on max effort, okay, yeah, it took 10 times the time and tokens, but it produced these stunning, realistic traffic patterns with the absolute best graphics. Cranking that dial literally transformed the output from clunky to completely beautiful.
Moving on to part 2, inside adaptive thinking. Let's see how Claude dynamically manages those tokens.
So we know Claude uses thinking, tools, and text tokens, but how does it actually juggle them all during a massive task? The evolution of how AI thinks is actually super neat. In the early days, we had the standard pattern. It was really rigid. The AI would think, then use a tool, then output text. Bam, bam, bam. Step 1, 2, 3. Then came interleaved thinking, where it got a bit smarter and could think a little bit in between tool calls. But the absolute new gold standard is adaptive thinking. In this setup, there are 0 constraints. Claude is completely free to think whenever, however, and in whatever order it needs to. It can output text to say I'm on it, pause to use a tool, think deeply about the result, and go right back to a tool. It's just total freedom.
And this brilliantly illustrates the difference between our old ways of prompting and this new effort dial. Historically, we had these legacy thinking toggles, which the source compares to forcing a teammate to turn their inner monologue entirely on or entirely off. I mean, that doesn't make any sense, right? With the effort dial, we are simply telling our teammate exactly how hard they need to try on a specific ticket. Our teammate still gets to decide when to think and what actions to take, but we set the baseline expectation for the effort required.
So the absolutely crucial point I want you to take away here is that adaptive thinking is not just some model router or automated toggle that classifies your query. No, it is giving the model the absolute freedom to leverage thinking dynamically at every single step of the process. Think about it. If you ask it what 2 plus 2 is, it's not going to waste time thinking, even if you set it to high effort. But if you hand it a massive, messy software architecture ticket, it will dynamically pause and think as much as it needs to. It maximizes its own intelligence based entirely on the task at hand.
All right, part 3, balancing speed, cost, and quality. Let's dial in our daily workflows.
Now this right here is where the rubber meets the road for us devs. Take a look at this trade-off curve mapping performance against token cost. You'll see a very distinct pattern. High effort gives really solid performance. Extra high pushes that even further. But look over at max effort. It demands vastly more tokens and time, and you really start to see diminishing returns in performance. Look, for some rare edge cases, sure, you might want absolute peak intelligence regardless of the cost. But for the vast majority of our day-to-day coding tasks, jumping all the way to max just might not be worth the massive wait time.
Because of those diminishing returns, here's a quick cheat sheet for the effort settings we have available. Max is strictly for your absolute hardest intelligence-bound problems. Extra high is generally the sweet spot for heavy coding and agentic workflows. High is a really great starting place if you're trying to balance token usage with intelligence. Medium is perfect for cost-sensitive work where you just need faster results. And low, that's for short-scope tasks where you are aggressively trying to save tokens and drop latency.
Actually, speaking of low effort, I just have to share this incredible anecdote from Anthropic to prove that low effort does not mean dumb. They actually had Claude play the video game Pokemon Red. On low effort, you'd probably expect it to just, play terribly. But instead, Claude acted exactly like a human speedrunner. It intentionally skipped trainer battles, it used healing items from its inventory to avoid having to walk all the way to Pokemon centers, and it spammed repel items to skip random encounters completely. It was aggressively trying to save tokens and finish fast. That's a highly intelligent, hyper-efficient strategy, not a stupid one.
Okay, part 4. Large models versus small models. The ultimate team matchup.
So, this begs the question, how do we actually choose between running a massive model on low effort versus a smaller model on high effort? Well, here is the golden heuristic from the source that you need to remember. Use a small model, something like Haiku, when you need bulk classification, simple summaries, and most importantly, a fast time to first token, meaning it starts typing its answer almost instantly. It's cheap, it's immediate, but use a big model, like Opus, on low effort when you have a complex, intelligence-demanding task that still needs speed. A big model on low effort might end up costing the same as a small model on max effort, but because of its higher baseline intelligence, it almost always gives you a much better time to last token, meaning it actually finishes the whole complex job faster.
Finally, part 5, best practices for coding. Let's outline our new standard operating procedure.
Let's bring all this theory right back to our daily stand-ups. Here is our dev team SOP moving forward. Step 1. Enable thinking whenever possible. Claude really needs that internal scratchpad to reason through our complex architecture. Step 2. Leverage task budgets. This is a genuinely brilliant feature where you can tell Claude, hey, do not spend more than 100,000 tokens before stopping to check in with me. It completely caps our costs and prevents those awful runaway tasks. And step 3, always run your valuations, chart your performance curves, and please actually read the transcripts. Just like we saw with that Pokemon speedrun, Claude might take some incredibly clever but totally unexpected shortcuts on lower effort levels, so you really need to read how it's getting to its answers.
But listen, if you remember absolutely nothing else from this huddle today, just remember this direct quote from the product manager at Anthropic. If you're working on anything coding and software engineering related, my advice would be go with extra high. It perfectly avoids the steep diminishing returns of the max setting, but it still gives Claude enough compute to dynamically navigate the deep, messy complexities of our codebase. It is literally the absolute best bang for our buck. So, as we wrap up this explainer and head back to our IDEs, I want you to use these guidelines. Ask yourself, which sprint ticket are you going to tackle first using the extra high effort dial? But this whole thing does leave us with a fascinating, kind of crazy, bigger question to ponder. As we give AI the ability to dynamically manage its own token budgets and think longer and harder on complex architecture, what will the role of the human engineer look like a few years from now? Definitely something to chew on. Catch you all in the repo.